Hello. So today we gonna cover the on-chain signature verification. It's a very straightforward topic, but it took me a while, a few hours to get it correct. So I'm just gonna share some code and also a few links to make life easier for you maybe. And the credit goes to this article over here. And I'm gonna leave the link in the description. So this is kind of like one of the application that we could use this mechanism for the NFT whitelist. And so we don't like waste thousands of dollars to write the address on chain. And instead, we just do the on-chain signature verification. And there are a few other examples in Solidity official documents. You can check it out here. And for payment channel and verifying signatures. And the algorithm it's used behind it is called ECDSA, or elliptic curve point manipulation. And yeah, check it out. And this algorithm basically only for signature verification. It's different than the encryption. So outline pretty straightforward. We're gonna sign a message and we're gonna verify it on chain. Okay. And to sign a message off chain, there's no interaction with the blockchain, and it could be stored using a database, and the format is just like the wallet address to the signature. So the user could pull the signature from your database and then use that to verify the signature in the smart contracts. And those are the steps we're gonna do. So we're gonna have a contract address and the user wallet address. The reason we have the contract address is so that the signature will not be able to reused in another contract by the same signer. And then we convert it to a hash. We get the interarray of the hash, and this I'm gonna explain it later. Then we get the signature. And when we verify it, basically we just need to construct the message on chain. So when the user comes to our smart contracts, we take the user's address and we take the smart contract's address. We construct the message on chain, and then we just like we could use some library. We could write our own code, but like with the Open Zeppelin library, it's like it does all those security check for us. So it's much simpler, I think. And the steps is like we have the signature, and then we construct the hash. We append some message. It kind of indicates that it's Ethereum signature. Then we can recover what is the user's account from the signature. Okay, we don't need this line here. Just ignore this line. Okay. Okay, and then, so first, I have the smart contract over here. It's a very simple one, just a few lines. And you can also find the smart contract in the code here. And here is the one with like its import library. And if you look at the flattened one, it's like all flattened in one file. It's easier to use. Then we deploy this, it's compiled. So then we deploy this smart contract. Signature demo. We deploy it to the testnet. And after we deploy it, and we're gonna have a contract address. We copy this contract address, paste it over here. So the first part is a contract address. The second part, we're going to use the user that we add them to, say, for example, the whitelist. Okay, so the user's address, we're going to use some random user. For example, this guy here. Yeah, you can be, I'm going to push the code to GitHub so you can just like go through the code and see what's going on. And the purpose of the video is just kind of show you like everything works. Okay. And yeah, and then in the code over here, we're going to connect to the wallet, and we're going to use our account 1 because we want to use account 1 as a signer. And we have different ways of signing it. They are like very similar. If you want to sign with MetaMask, like every time when you sign, MetaMask can ask you permission for signing it. And the code is this part. So basically, you create those message and use this KE CAC 256 function to hash it. After you hash it, you verify the message. And the reason you need a verify is like when you sign it, it must take a 32 int array. And it has a link to explain things here. I'm gonna attach the link in the description too, just read through it. Then it signs the message for you. So go back here. When we click, I'm gonna open this console log. Where's my console log? Gonna open the console log here. Okay, for some reason it's not opening. I'm just switch another window. Okay. All right. So when I click sign with MetaMask, you'll see the first one is our message, and the second one is like the array representation of this message. And MetaMask pops up a window, asks for the permission to sign it. When we click sign, it gives us this string, which is the signed string. We copy the string, go back here. We paste the string over here, and we're gonna give it, so right now we log in to our owner account, but the message is signed using another account, which is our account 3 over here, okay? So if we use our owner account and we click verify the message, we're gonna get false. The reason is in the smart contracts, when we construct the message, we take the message sender and also the address of the smart contract. This means the smart contracts. And then we take the address of the smart contracts, okay? And which is not correct. It's not the same message as our original one. So if we log in to the account 3, you see 602, which is same as this one, 602 here. Then we click verify. This time we got true because we have the same message here, and then it verifies the signature. It recovers the signer, and you can see the signer here is our owner's account. So that's kind of how everything works. I don't know if it's explained well. And another way to do it is you could just write a function that just automatically sign it without MetaMask. And you see this function, the same as this function. The only difference is you need to create a signer and pass in your private key. So then you do not have to give your authorization every time. You can just like write a for loop and then sign, I don't know, sign a address like in a CSV or whatever. And to get your private key, is go to your MetaMask. And here, account details, export private key, enter your password, and here you go. So all you need to do here is just replace this guy, remove this with your private key. That's it, okay? And just gonna show you when I click here, it's gonna using the private key because the private key I provided is the first account. So it's gonna sign the message exactly the same as when we sign it with MetaMask, okay? And for example, if we switch the account to account 3, and then we sign it with MetaMask, you'll see that we got a different message because the signer has changed. And for the smart contract over here, it's not doing anything fancy. Basically, it creates, like we mentioned before, it's construct a message, and it's use the Open Zeppelin library to ECDSA to recover the signer. And it's really not doing, it's like it helps us to cover all those like security cases like over here. And in the end, it's only called this one. It's called this function, EC recover, and it's just gonna recover the signer. This is like a Solidity or Ethereum reserved function. So yeah, that's pretty much it. And to prove that we really signed it, so if I go, this is like the signer's account, and I'm gonna copy the signature. Okay, signature, and this is the original message, and then we verify it. You can see it's verified. And if we change any of this, it's not going to be verified. So if we go to account 3, then you see the signature is verification failed. Okay, yeah, I hope it's clear. And yeah, let me know if you have any questions. You can ask them in the comments. And